Okay, in the last lecture we worked and we developed this equation for the steady state error. Okay, and remember that's what our discussion is about. We're looking at steady state error as opposed to transient response, which is what we've been concentrating on up to this point. How to get the system to go where we want it to go quickly and efficiently. And we've changed gears a little bit here, and now we're thinking about what does the system do when it gets to that point, to our set point. Does it get all the way to the set point? Does it get exactly to the set point? Does it stay on the set point? What is the steady state error associated with our system? And this is important when we're looking at what we call follower systems or follower controllers, where we want we're not going to be changing our input around a whole lot. We just set it and we want the system to stay there. Of course, the classic example would be an oven. We set it at 350. We want it to go to 350, and we want it to stay at 350. And so that's the type of system we're working with here. And we developed this equation here that gives us the value of the error at infinity, or the steady state error. And we did a short little example about that using that equation. This is the general case, and you can always use it, but it's a bit cumbersome in some cases. And so in this lecture we're going to try to pare it down to some of these more specific cases and try to get a more of an understanding of it rather than just an equation. And so what we're going to be doing is looking at specific types of inputs. We're going to be looking at the step input, the ramp input, and the parabolic that I mentioned a couple lectures ago. And with these three conditions, or these inputs, we can get a pretty good sense of what the system's going to do and whether it's going to perform adequately in the application that we have. And so this is a very simple substitution. We take our general equation and we put our input of a step in there, and we go through the math for that, and we end up for the step of this equation here. The steady state error for a step input is 1 over 1 plus the limit of s goes to 0 of g of s. And we can do the same thing for the ramp input. The input is 1 over s squared. We substitute that into the equation, and what we end up with is an equation, the limit of 1 over the limit of s times g of s as s goes to 0. And then, of course, the third one is again very similar, but our input changes to s cubed, and as we work down through this, we end up with this equation. Okay, so now these move from our general case that will work in all cases to an equation for the step, and an equation for the ramp, and then an equation for the parabola. So we can use these as shortcuts for these specific cases if we want to calculate the steady state error for those specific cases. All right, so let's look at a specific little case in here and see if we can find the answer to that using this. Okay, and so that's not going to work, and so we'll just plunge ahead without that. But anyway, so what we've got here is an input 5t unit step, and so that's actually a ramp of magnitude 5, and then we've got a simple open loop transfer function, as you can see in here. So what we're looking for is our equation for a ramp, and so our error in this case, error at infinity, is going to be equal to 1 over the limit of s goes to 0 of s g of s. Okay, I'm just simply copying this down here. Okay, so in our specific case here, we have 1 over the limit of as s goes to 0 of s, and our g of s, 100, s plus 2, s plus 6, and s plus 3, and s plus 4. Okay? So we have that. Now we're going to do some simplification, and when we do our limits, all these s's will go to 0, and what we end up with is 1 over 100 times 2 times 6 divided by 3 times 4, and we keep working through that and simplify that. I did this before, so it's equal to 1 over 100. And so we shortcut a little bit on here, and we find out that the error at infinity, steady state error, is equal to 1 over 100 for this ramp input for this particular open loop or closed loop system. So that's how we would apply these three specific cases for the step, the ramp, and the parabola that we derive from the general case up here. Okay? Now, I want you to think about this a little bit. Okay, what our goal here is to get 0 steady state error, right? That's what we would like. We want our system to follow our input with high fidelity, and so we want it to go to exactly what our set point is and stay there exactly. So a 0 steady state error is optimum for this. So I've gone through and worked out some different cases for us, and hopefully you can see a trend here, and from that trend we can figure out what we need to do to the system in order to achieve this. Okay, so I'm going to make this a little smaller so we can get all these in here at one time. Alright, so this is a bunch of scribbling here, and what I've done is I've taken this case and worked it down through here for the step and for the ramp and for the parabola, and I've done the same thing for this case and for this case. Alright, now they're the same, they're similar G of S's. Okay, if you look at this case, our G of S is equal to 1 over S plus 2, and in this case 2, we've got 1 over S times S plus 2. We've got a free integrator in here. A free integrator. This is going to play a big role in this. And here in the third case, we've got a free integrator squared. Okay, 2 free integrators in there. Okay, now so let's look down here and see what happens to our system as we subject it to a step input. Well, for a ramp, or for a step input in here with our first case, we get a finite error. Okay, finite error. Now, when we subject that to a ramp input, we get an infinite error. It doesn't keep up. It keeps diverging. Our input goes one way, and our system never catches up. It actually falls behind, and we get an infinite error at infinity. Same thing with the parabola. We get an infinite error. Now, let's look at this next case where we've got the 1 free integrator in here. Look what happens with the step input. We get a 0 steady state error. That free integrator, that integration term in there, snugs it up and draws it into a 0 steady state error for a step input. Now, with a ramp, the input's running away from the system, and so we don't catch it, but we stay up with it. Okay, we have a finite steady state error in this case of a ramp input with a single free integrator, and then the parabolic, we're back to infinity again. Okay, and let's look at the third case where we've got two free integrators in here. We've got a zero steady state error. That integration works doubly well in that, and so we end up with a zero steady state error for our step input and a zero steady state error for our ramp input. And then if we go through the calculations, what I didn't do, we end up with a constant steady state error for our parabola. Okay, so we see a direct relationship between the number of free integrators and the order of the input, whether step, ramp, or parabola, and being able to create a zero steady state error. You'll see in these cases here, zero steady state error. In these cases here, we get a infinity, and then in these cases here, we get a constant steady state error. Okay, so this gives us some insight into what has to happen in order to achieve reduce our steady state error. We've got to add free integrators. Okay, free integrators. Okay, we've got to add a k. We've got to add a ki over s terms, and maybe more than one, maybe a couple of integrators in there. We've got to add this in our controller if we want to minimize a steady state error. So, as I've told you before, the big claim to fame for a integrator term in our controller is to reduce the steady state error, and this is how it's doing it. Follow through the math, and it comes out just like we discussed in our hand waving. It shows us that yes, indeed, adding free integrators does reduce the steady state error and sometimes completely eliminate it. Now, a little word of caution here. Let's look at what happens with this system in here. Okay, as far as our root locus is concerned. So we've got a pole here at 2, and we've got a couple of poles here at 0. Okay, looking and drawing our free integrator in there, or our root locus in here. We've got one branch going here. We've got three branches going to infinity. So we know we've got some asymptotic lines in here somewhere like this, which means these two guys are going to come off like this. Go to infinity. All right. So yes, we achieved a zero steady state error, but what we've done here is create a very marginal system, because at low gains it would be a zero steady state error, but if we start increasing the gain just even a fraction, we will pull this into instability, and that's one of the downfalls of an integrator. Okay, it leads to instability because it pulls the root locus to the left or to the right, to the unstable. Now, depending on how this works, these could come out here like this and go like this, and we could get a little bit of an opportunity to have a stable system in there. But you got to be really careful with this. You can't just look at the free integrator alone. You've got to look at what it's doing to your root locus and the stability of the system, the speed of the system, and blend that in with an overall solution to your problem. Okay? So that is end of this lecture, and we'll boil it down and make it even a little easier for you next time.